Welcome back. In the next part of this lecture, we're going to learn some more theorems that will help streamline the whole limit finding process. So we've already learned with rational functions and polynomials that you can find limits by direct substitution. For rational functions, you had to have that the denominator wasn't zero. So what we could really say is anywhere inside the domain for a rational function, you could find a limit by direct substitution. And for polynomials, in their whole domain, same thing is true. As it turns out, that's also true for radical functions. So for any real number, if you're looking at an odd root, the limit as x goes to c is just found by taking that odd root of c. If you've got an even root, of course, you can only take even roots of numbers that are not negative. So if you're looking at limits as x goes to c, then c would have to be something that's positive. Of course, the thing that we have to make a careful note of here, your even root function, the domain is from 0 onwards, but you wouldn't be able to find a limit at 0 because, of course, for a limit to exist, there would have to be something on either side of that point. So for example, with the square root graph, there's nothing on the left side of 0, so there'd be no limit for that as x goes to 0, but for any other number that's larger than 0, yes, the limit will exist, and that you can find it again by direct substitution. So for this, I'm going to do a little bit of less writing. I'm still going to do some writing, but I'm going to just make a few notes here. So number one, I notice that for the denominator that I've got myself a polynomial, and I know for polynomials I can always evaluate them, directly substitute in to find what the limit is. So I know for x squared minus 1, I know that the limit as x goes to 4 is 15. The other thing that I know for the numerator is that I've got root of x plus 2, and I know for the square root function I can find the limit just by direct substitution because it's an even root, but I'm looking for x going to some positive number, so I'm good there. And square root of x plus 2, the limit would just be the limit for the square root of x plus 2. That's something, of course, not too hard to see. So combining some previous theorems, I could say, well, the addition rule tells me that if I'm looking for two things added, I would add the two limits, and that the limit for square root of x as x goes to 4 would be square root of 4, and the limit for 2 would be 2. So we wind up with square root of 4 plus 2, or 2 plus 2, which is 4. And so now I can finally answer the question, which is what's the limit as x goes to 4 of root of x plus 2 over x squared minus 1, and the answer is 4/15. I just evaluated the top and the bottom. The bottom wasn't 0, so we were good to go just by direct substitution. Trig functions as well. Anything that's inside their domain, that's a point where you can find a limit by direct substitution. So if we're talking about sine and cosine, that's everywhere. The other four trig functions, they all have places where they've got gaps in their domains. So everywhere except for that. So for example, tangent, it has asymptotes at pi over 2 and 3 pi over 2 and so on. But everywhere else, the limits would exist. And so for any trig function, we can find limits just by direct substitution, as long as we're looking at something inside the domain. So if I'm looking at this, I can see that I've got a trig function made out of sine and tangent. So again, I'm going to do less writing here because I don't really need to justify each and every step, but I'll just sort of verbally say it out loud. I know that at pi over 3, I could find the limit for sine, and so as a result, you should be able to find the limit for sine times sine, or in other words, sine squared, just by substituting. And of course, a constant multiple times sine squared, you would just multiply that constant. Tangent. I know tangent pi over 3 is inside of its domain, so the limit for tangent I could find by substituting. And if I can find the limit for tangent, then I can find the limit for tangent squared. So in other words, I can find the limit for everybody just by doing direct substitution. So here, now I'm going to do way less writing than ever before, and I'm going to say I've already cleared it through just sort of mentally that I can find these things all by direct substitution, that pi over 3 happens to be in the domains of all of those functions. And so I'm ready to go and say, well, I know for sine squared of pi over 3 and tangent squared of pi over 3, that's what I would get when I find my limit. So I would have 8 times sine squared of pi over 3 minus tangent squared of pi over 3. So sine squared of pi over 3, sine is root 3 over 2, so that's root 3 over 2 squared. And tangent of pi over 3 is root 3. So we have root 3 squared. So we wind up getting 3 as our final result. So because we were looking at a trig function, something made out of trig functions, and at a point that's inside the domain of that trig function, then we can find that limit by direct substitution. Composite functions. So, of course, we don't always just deal with sine of x. Maybe you're dealing with sine of square root of x. Or maybe you're dealing with not just square root of x. Maybe you're dealing with square root of x minus 2. Something where there's an inside function and an outside function. This theorem is telling us basically for limits, provided that the limits exist all the way along the way, we work our way from inside to out. So here, the function that we're looking at, f composed with g is the inside function. So if we're looking at the limit as x goes to c of this composite function, if the inside function has a limit, and if what that inside function is going to, if that limit exists for f, then you can basically find your limit by direct substitution, substituting into the inside function, evaluating that, and sticking it into the outside function. So basically, we just have to ask ourselves, if I were to substitute in that value in for x, is that a function where that limit would exist? Would that be something where I could do direct substitution? So let's take a look at an example of that here. I've got this function cosecant of x squared minus 2x times pi over 4, and I'm looking for the limit as x goes to 3. So first off, there's again two functions. There's y is equal to cosecant of u, and then there's the inside function, which is the x squared minus 2x times pi over 4. So what we have to ask ourselves is, for the limit of cosecant of u, cosecant of this inside function, number one, does the limit exist for the inside function? So if I look at the limit as x goes to 3 of x squared minus 2x times pi over 4, does that limit exist? And I would say, well, for sure it does, because this is a polynomial times a constant, so I can definitely find that limit, and I can find it just by direct substitution. I can put in 3 for x, and I can say, great, so we'd get 3 squared minus 2 times 3 times pi over 4, or in other words, we would get 9 minus 6, we'd have 3 pi over 4. So as x goes to pi over 3, u goes to 3 pi over 4, and I ask myself, for cosecant of u, what happens as u goes to 3 pi over 4? Does that limit exist? So I need to remember for myself that for cosecant, that it's got its vertical asymptotes at places like 0 and pi and 2 pi and 3 pi and all the negative ones of those. So that means that 3 pi over 4 is definitely inside of its domain. So if I were looking at the limit as u goes to 3 pi over 4 of cosecant u, I would say, well, that's definitely a thing, and what that happens to be is root of 2. And I find that by direct substitution. I calculate out what cosecant of 3 pi over 4 is. That's the same thing as 1 over sine of 3 pi over 4, which turns out to be just root 2. So the inside function, the limit exists as x goes to 3, and what this thing is going to, that limit exists for cosecant. So for my big conclusion, I can now say, well, for our limit as x goes to 3 of cosecant of x squared minus 2x times pi over 4, that limit is basically found by, again, direct substitution, that when you put 3 in, the inside becomes 3 pi over 4, and cosecant of 3 pi over 4 becomes root of 2. Okay, another good thing to note here, this is sort of feels like a funny function, a funny theorem, but it has a very good reason for existing, and we're going to see the reason in just a moment here. So these are two functions that agree at all but one point. So you've got two functions that are identical. They're identical for everything except for one particular point, and that point is x equals c. So if you're looking at the graphs, you might have the graph of f looks like this, and then the graph of g looks identical except, and I'm trying to draw it identical, except maybe at C it's doing something different. Maybe there's a skip or a hole or a jump or whatever, but everywhere else the other functions are identical to each other. So the thing that it's telling you is that if the limit exists for the one function, then the limit will exist for the other function. And then the two limits would have to be the same. So in other words, if you have two functions that are identical except at one point, if you can show that the limit exists for one, then the limit would have to exist for the other, and they would have to be the same. It would be the same limit. This is at that point that they're different at. So I've got these two functions here, and hopefully this is sort of the reason why we've got this lovely theorem. If you were looking at these two functions, f of x and g of x, the one thing you'd notice is that they're almost identical to each other. If I look at g of x and I were thinking about its domain should be all real numbers. And that it's a nice polynomial, and so limits we can find by doing direct substitution, and everything's wonderful, as opposed to f of x, where it's a rational function and it's got a domain with one little excluded value in it, and that's the value of 2. So you would not be able to find out what is f of 2. So if you were looking for the domain, it's everything up to 2 and everything after 2, but not including 2. So you couldn't figure out what f of 2 is. You can definitely figure out what g of 2 is. It's a polynomial. You can always put in that number. But for f, it's not defined at 2. Now, the good thing to note, of course, is that these functions are the same except for at 2, because if you're looking at f of x, of course, the x minus 2's would cancel. So really, f could be simplified to show that it's the same thing as g, but again, the difference would be that f would still be not defined at 2, and g is definitely okay to be at 2. That's totally fine. So that means if you were looking for the limit as x goes to 2 for f of x, you could say, well, instead, if I looked at the limit as x goes to 2 for g of x, that's something I can easily calculate because that's a polynomial. It's a polynomial. You find limits by direct substitution, so its limit has got to be 1. These two functions are the same everywhere except for at 2. So since g has a limit and its limit exists and is 1, then for f of x, its limit must exist and should also be 1 as well.